All right, let's dive into one of the oldest and honestly one of the most powerful manufacturing processes out there. We're talking about a technique that literally turns liquid fire into the solid objects that build our entire world. Let's get right into it.
Okay, take a good look at this. This is the engine block from a V6, the very heart of a high-performance car. I mean, it looks like it's been carved from one single massive piece of metal, right? It's got all these intricate passages, those perfectly formed cylinders. It's just a marvel of engineering. But how on earth do they actually make it?
So how is it possible to create something so incredibly complex from what looks like a single piece? Well, it's not carved, and it's definitely not welded together from a bunch of smaller parts. The secret is, it's basically grown from a liquid, using this amazing ancient art called casting.
So casting, sometimes it's called founding, is really about one thing. You take metal, you melt it down into a liquid, and then you pour it into a cavity, a mold that has the exact shape you want. Once it cools down and gets solid again, boom, you've got your part. I know, it sounds super simple, but trust me, the elegance is all in the details.
You can actually boil the whole process down to 3 really simple steps. First, you start with a model. That's a positive replica of what you want to make, kind of like this rubber duck here. Second, you create a mold around it, which is the negative space, the empty shape of the duck. And finally, you pour in your liquid material to create the final cast piece. We're going to use this exact same principle, but, with scorching hot liquid metal instead of rubber.
Okay, so to make something as incredibly complex as that engine block we saw, you can't just use any old mold. Manufacturers use a special technique called sand casting. So let's take a look at how simple sand and, liquid fire come together to create these amazing pieces of precision engineering. All right, this diagram here is basically a roadmap. It's a cross-section of a typical sand mold. Now, I know it looks a little complicated, but every single part you see here plays an absolutely crucial role in taming that molten metal. So let's break it down and look at the key features. First up, we have the core, and this is a truly brilliant idea. It's a separate shape that you place inside the main mold to create hollow sections. So think back to our engine block, right? Those perfectly round cylinders where the pistons go up and down, they're formed by these cores. Without them, you just end up with a useless solid block of metal. Okay, next problem. You've got to get all that liquid metal into the mold. And you can't just, dump it in. That would be a disaster. You need a really controlled delivery system. And that's where the gating system comes in. Think of it like plumbing for molten metal. It starts at the pouring cup, flows down the sprue, and then along the runner. It's all designed to guide the metal in smoothly without any splashing or turbulence. Now this brings us to a major challenge in casting, and that's shrinkage. See, as metal cools down, it contracts, it gets smaller. If you're not careful, that can leave empty pockets or voids inside your part. That's where the riser comes in. It's basically an extra tank, a reservoir of molten metal that keeps feeding the main casting as it shrinks. It tops it off, making sure the final part is 100% solid. And yeah, let's talk about that liquid fire part for a second. The temperatures we're dealing with here are just staggering. Take a look at aluminum. This is what they use to make those awesome-looking car rims. It's poured at up to 750 degrees Celsius. But that's nothing. For a classic engine block made of gray cast iron, you were talking about pouring liquid metal at almost 1600 degrees Celsius. I mean, that is literally hotter than lava. So you might be asking, why pour it so much hotter than its melting point? Well, there's a really good reason. It's a critical step called superheating. That extra bit of heat acts like a buffer. It gives the metal the fluidity and, just as important, the time it needs to flow through that whole gating system and fill every single tiny nook and cranny of the mold. Like the really intricate spokes on a complex car rim, before it even thinks about starting to get solid. But look, with these insane temperatures and really complex fluid dynamics, it's no surprise that things can, and definitely do, go wrong. This is where the art of casting really meets the science. It's why modern foundries use these incredibly powerful computer simulations to predict exactly how the heat and liquid will flow so they can get it right before a single drop of metal is ever poured. So here's a classic example of a defect. This one's called a misrun, and it's pretty much exactly what it sounds like. The metal just didn't complete its run. It solidified too early, before it could fill the entire mold, and what you're left with is an incomplete and totally useless part. So what causes something like this? Well, it all comes back to the stuff we just talked about. Maybe the pouring temperature was too low, right? Not enough superheat.
Or maybe the gating system itself was designed poorly, and it slowed down the flow. It could even be that some sections of the mold are just too thin, and the metal cooled down the instant it touched them. It really is a delicate dance between heat and speed.
Okay, now let's look at another really common problem. This one is called a hot tear. This isn't about an incomplete part. This is a part that has literally torn itself apart while it was cooling down. You end up with these nasty-looking cracks, and you often see them at corners or where a thick part of the casting meets a thin part.
And the cause for this is actually fascinating. It's something called hindered contraction. So as that hot metal solidifies, it naturally wants to shrink, right? But the sand mold is rigid. It's holding it in place, fighting against it. This creates this incredible tension inside the metal, which is still hot and relatively weak. If that tension becomes stronger than the metal itself, it just rips apart. It's literally a battle between the casting and the mold.
So you can see there are challenges, for sure, but when it's done right, casting is responsible for some of the most critical and complex parts in our modern world, and it goes way beyond just cars.
I mean, we've talked a lot about engine blocks and car rims, but this exact same fundamental process is used to create everything from the super precise turbine blades you find in jet engines to the beefy casings for huge industrial motors. You'll find it in massive flywheels and even in the parts of the machines that build other machines. Seriously, casting is truly everywhere.
So, the next time you hop in your car or really just look around your house, I want you to think about this ancient process. Take a second to look at all the complex metal objects that we just take for granted every day, and ask yourself a question. What object near me right now started its life as liquid fire, poured into a mold, just to become the shape it is today? I think you'll be surprised by what you find.